Okay, I believe the recording has started for all. Okay, so I think let's get started. We are a minute past. So we have the following are the topics for discussion today. Today's session is important because your assignment will be coming up as I have announced on Canvas. So yeah, so I will cover that topic that is critical for your assignment, and your assignment is will be till for about 25 odd days. I think I'll launch it in a couple of days until end of this month. So midway through that, or about 10 days from that, we will anyway have a webinar. So I'll give you about 10 days to think through, start implementing. It won't be that complex. It'll be based on what we do in class. But I will, around 15th, we'll have a webinar where we'll meet for an hour or so, and we'll go through some discussion about the assignment itself. So if you have any questions regarding assignment, we can discuss then. But I kept it on 15th because you have 10 days to kind of start working on the design, implementing some things. And then after the assignment, you have 2 weeks to finish off. After the webinar, you have still 2 weeks to kind of refine anything and finish off the assignment. Okay. So if you see the screen, so what we will do is we will first cover a couple of topics which were left from the previous session. We were talking about parallel distributed systems, right? So we'll talk about some example architectures, and we talked about UMA machines or and non-uniform memory access machines. So we'll talk about some examples from there, and then we'll talk about shared memory versus message passing, and that will bring us to a discussion of uh, today's primary topic about designing parallel programs. And there uh, we will talk about some message passing primitives. OpenMPI is an example library that you will use for implementing a message passing application, which means you will have bunch of processes running on one or across machines, right? And doing something useful. So this is your first example of a parallel processing application and using this library. Now, there are ways to speed up that using multi-threading on one single node as well. If we have time today, we will start on this, talking about multi-threading and OpenMP as a way of implementing multi-threaded programs, but it's not so critical for your assignment. So if we finish it today, great. Otherwise, we'll take it up next week. But what I want to do today is kind of start off with what kind of parallel architectures are there, and an example of writing a parallel program using OpenMPI library. That's the library that you will use for writing your first parallel program, I believe. So I'll give you a use case and you have to write a parallel program to implement it. Now, that could be done on your laptop because your laptop is a parallel computer. It has multiple cores. Or you could choose to use a cluster of machines. Like you could get 2, 3 VMs, get a bunch of VMs maybe in the bits lab or anywhere else, and then you can implement it. But your assignment will be primarily to show that you can write a multi-process program communicating using OpenMPI and doing something useful, like a data analytics use case, let's say. Okay, so first things first, let's talk about, let's close off the discussion on parallel distributed systems in terms of different hardware architectures before we get into the software side of things. So there are, very broadly speaking, two types of machines we are talking about. One is multiprocessor, other is multi-computer systems. Multiprocessor essentially, you can think of a uniform memory access multiprocessor. So think of processors on one side, there is some sort of an interconnection network, and there is shared memory to access on the other side. So every processor goes through the same interconnection network to connect to some memory bank. And there is nothing local on the processor. So all memory is kind of going across this interconnection network. So you can think of every processor accessing memory will have sort of the equal amount of time spent or same latency or same complexity in accessing memory on the other side, no matter which processor it is and where the data item is located. Because this interconnection network is fairly regular in structure. So to access any piece of memory from a processor, it may take same amount of time, right? That's why it's called uniform memory access. And typically on the software side, I'll distinguish again later today that shared memory address space is a little different from saying shared memory. Shared memory address space means that when you're writing a program, the program, one component of the program or one process running the program could be running on any processor. However, they get a shared view of the memory. So let's say your memory addresses are like 1 to 64 million, right? Assume that. So from any processor you can access that whole 64 million size address space. You don't care physically that is that address located in memory 1 or memory 2 or memory 3 bank, where is it, right? So, and shared memory means all processors can access all memory banks in hardware in the same way. That's called shared memory. But shared address means that you could be actually from any processor, any piece of software will be able to access any memory. So that's very different from hardware and software standpoint. We'll clarify that again later, because it is possible that even though you may not have the equal or uniform access from every processor to every memory, you can still build a shared address space. You can actually build a shared address space over message passing systems also. But in this kind of a UMA architecture, uh, pretty much you will always have a shared memory address space. You will always write programs that can access this whole address space as if it belongs to everybody. There is no common clock. These have all separate clock chips typically, so you may have to implement in software some kind of clock synchronization if you want. Pretty fast interconnect because you're talking to memory, right? So it has to be pretty fast. You can't put an Ethernet here. And essentially, if you have a very large program and you want to improve performance, you want to partition the work across processors, you do this. So a lot of scientific computing applications may have this kind of an architecture. Uh, Now, a little bit improvement of that is that if you have a cache also. So I've highlighted this. So even though your memory is all here, but you could implement caches that are very close to the processor just to speed things up. So if your data is sitting in your local cache, it will be faster. But if you're accessing remote memory, you have to go through the interconnection network. Most of your symmetric multiprocessors are built this way. So even the hardware that where you run on most of the machines that you use are typically SMP systems, right? They have memory banks, they have processors with caches, and they will go across an high-speed interconnection network. Now, if you look at a multi-computer system, that will look a little different. You will notice that there is no uniform. Okay, symmetric multiprocessor means because so you'd see that this looks fairly symmetric in structure, right? Because UMA is a very symmetric environment, right? Where you have uniform access from a processor to memory. No matter where your code is, it's not that this processor one has more latency going to memory one or less latency going to memory two. It's not like that. So when you build this kind of an architecture, it is typically very symmetric in nature. No common clock means that when you cannot assume that most of these programs, there's no single clock chip that is driving uh, the timing across all these processors. Typically, that doesn't happen. You can have your own clock chips. So why I'm saying is because when you write programs on a system like this, you cannot assume that at a microsecond, nanosecond level that there is timing synchronization between the code. Because if you measure time on a processor to do an activity, you cannot say that it's exactly the same time on the other processor. That assumption in programming you may not make. It depends on the hardware. Sometimes they do, but many times they don't have a common clock. It's fairly important when you write parallel programs or distributed programs, because if your program assumes some kind of timing behavior, you cannot assume that every piece of code running across these processors will actually see time at a nanosecond level at the same time. Okay. So you may have to do something in software, or you have to devise your algorithm that is not so time sensitive. So if you happen to take a distributed computing kind of course, you will understand that how important is it to when you write a parallel or distributed program to make sure that you understand that time is not the same on every piece of code running on different processors. So example, I read write data to a database. The reads and writes are happening across processors. You cannot assume that when I write something, everybody sees it at the same time. So you cannot assume that I write data and some other piece of code is reading data, they will be able to read at the same time. May not be possible. So in software, you have to take care of it. Okay. So timing is very important in writing distributed parallel programs. So that's what was meant by SMP. Now, when you go into a multi-computer system, you see that it's not that memory is remote somewhere and or across the network. Your network means maybe one chip having or on board having some kind of a high-speed interconnection network. So you may have so all the processors have local memory. The architecture looks like this, and there is an interconnection network. So why is it called NUMA, a non-uniform memory access? Because you see that I can go from this first processor here, I can go to local memory much faster than I can go over the interconnection network to another processor's memory, right? So that is why it is called non-uniform memory access. Now, it is still possible that you have a shared address space. So this is what is different from shared memory. So this is not a shared memory system, but in software, you can still make it so that it looks like a shared address space. Either software or sometimes in hardware NUMA, where it's like you can have an embedded hardware level wiring or some kind of a microcode running, so that when you write a program, it kind of automatically accesses data from another memory and brings it to the local memory of the processor, right? But most of the times you can also encounter a software NUMA, where the operating system has to make sure that the memories, when you are accessing something that is on different memory, it fetches the data from there. And this is where message passing comes in, right? So in software, you're going to fetch data from another machine, but the program that you're writing may not know. That's why we will study OpenMPI next, which is a message passing library where the send and receive calls actually fetch data from other machines or send data to other machines under the covers. Again, definitely no common clock. This is an important term also. You should know that something called CC NUMA or cache coherency. CC is for cache coherency. So remember, whenever you have caches like this and you have remote memory, right? So what will happen is, let's say this processor, the second processor from the top, has written some data into its local memory, which has of course changed the cache as well, right, on this processor. However, on the first processor on top, I write some code which will access this data that is lying on the second processor. So my cache, right, my local cache and my local memory does not have the updated copy. Now, uh, if you have some sort of a cache coherency built into the hardware of a NUMA machine, this data will be automatically kind of either brought in, or maybe this data in this cache of processor one on this top processor may be invalidated, so that an explicit read from the other processor happens, right? So what can happen is that you write here on this processor is write happens and you are reading from here. Maybe the data already resides in the cache of this processor. So maybe the data is sitting here, right? This is old data, right? Whereas some new data has been written into this with the same data item. Now, CC-NUMA means these caches have to be kept coherent. So in these machines in hardware, uh, invalidation signals will be sent so that this data, old data, will be marked as old so that this top processor, when it reads, it will be forced to read data from the other piece of memory. So this term you will encounter often called cache coherency or CC-NUMA machines. Okay. Otherwise, you have to do all this in software, right? If the machine doesn't do it for you, then you have to, in your code, in software, kind of go and check, is this data old? And then I should make a receive call to get data from the second processor, and data has to be brought in. Right? You can always do it in software as well. But anything you do in software at a higher level will be slower. So Amol, in your question in multiprocessor environments, what bus interconnect refers to and how it works. I mean, we won't get into the hardware of that, but you will find different kinds of interconnection networks. The most expensive one is a cross-point switch. I think I discussed it in a previous class, where every point connects to every other point. So it's a single hop, very fast, but it's very expensive. Or you can have a bus, where bus is a shared, it's like a think of a bus system means that only one person can send a signal, right, from one point to the other because shared. So when somebody sends a signal, sends a data on the bus, nobody else can, right? Which means it's cheaper. It's like having a highway with one lane on it, right? Now, an expensive bus may have 4-lane highway, so it has 4 channels in the bus. Only 4 people can send data at any point of time. But what is the best case scenario? That I have n people, 100 people, 200 people who want to kind of send something, and all of them can because all of them have their own connections or pathways. That's a cross-point switch. That's the most expensive one. So when you build interconnection networks, it's always an optimization done in between a bus and a cross-point switch. Depends on how much money you want to spend on that particular network. Cheapest is a bus, slowest, but right, least expensive, more latency because you have to wait when others are sending receiving data. And expensive machines may have a cross point switch where anybody can send data at any point in time without colliding with others. So this is where let's discuss NUMA and UMA shared address space platform. So your distinction between these platforms is important from basically how you design algorithms. You can imagine this, right? Suppose you take this. Here you have studied locality of reference. You see, when this first processor, when I was reading data from it, I would assume that the data already resides here on its own local memory, which means if somebody else has written some data, but the data was already made available to the local memory of this first processor, my read would have been very efficient, which means I'm looking at locality of reference. So whenever I read data, can I get the local data local to my machine? Whereas if I was looking at this kind of an architecture, a UMA machine, I don't really care because anyway, I'm going over an interconnection network to access memory, right? So everybody has access to this memory. So somebody can write data into a memory location, but another processor will read from exactly the same location. They don't have copies, right? Only thing you have to take care of is that is there locking needed because we are reading writing the same address in memory. However, here it's a different problem. I have to look at locality of reference. So if I'm referring to data that is not locally on my machine, that means I'm wasting time going to other processors. So more locality of reference means better performance, right? So that you have to take care of and writing code on newer machines. That are you able to bring data local, or or can you kind of have a lot of temporal spatial locality in data, and only then newer machines will give you good performance. Otherwise, you're randomly accessing data all over memory, right? And always you're going over the network. So newer machines require locality so that you get the true benefit of parallelization. That's the main problem here. And of course, cache coherence is another problem in NUMA machines because you have copies of data now, right? So these are two things you have to be aware of. But NUMA machines are most common. It's asymmetric, right? So these machines typically are most common. If you extend these, so think of this architecture. If I replace this interconnection network with simply an Ethernet network, and these PCM, what you see, processor, cache, memory, and maybe some storage, all of it together, if it's one machine, this is nothing but a distributed system, right? Because it's not a single box computer, right? I can take each of these as different nodes and replace this interconnection network, the regular Ethernet. This is a most common distributed system you'll ever see. That's most commonly used. Any data analytics application you build, they will look like that. There'll be clusters where this is Ethernet and these are independent machines. That's why locality of reference, cache coherence will become very important then. So when you write data analytics applications, when you study Hadoop and Spark and all the systems later, they will be multi-computer systems where these are all commodity machines and interconnection network is nothing but an Ethernet. Just a cluster of machines. If you look at a scientific computing application, then you may use a multi-computer system where all of this is tightly coupled maybe into one big box with a very expensive interconnection network. Let's take some examples. So just so that you know that the real machines which are built like this, right? If you look at Intel Core i7, that's basically an SMP. That's why if you look at your laptop, that's an SMP machine most of the time, right? There's a big physical memory, right? And these are all these 4 cores using some on-chip network, right? This is probably a faster network on the chip. And then you go through a memory controller to the memory chips outside. So this is typical SMP because from every core going to memory is the same cost. And all the memory is shared here. It's a shared memory system. Let's take another SMP example. This is more of a server class machine. If you look at an UltraSpark T2, fairly old machine, but you see that bunch of processors, and they've used a crossbar switch here. So it's an expensive interconnection network where any processor can connect to any memory system parallelly. It's not a bus or an Omega network or something like that. It's a cross point switch. So that's why it's a server class machine. It's very fast interconnect. And you see that there's a cache associated with every memory. We already looked at this kind of an architecture here, right? Every there'll be a cache and there'll be some piece of memory. And processor will first hit the cache and then go to memory. This is something like that. Let's take a NUMA example. Many of, I've not named a specific machine here, but if you look at many of the modern dual socket configurations available, many of these motherboards, where you can basically put in 2 of these kind of cards, right? So you'll have 4 cores here going through memory controller accessing memory. So this one box is a shared memory system, but you can put 2 of these, right? And they will communicate over some specialized interconnection network on this motherboard, right? So if you want to fetch some data X sitting on this particular card, then you have to send a message and get it, right? So this is a typical example of a non-uniform memory access machine. So it's faster to access X from cores 1, 2, 3, 4. It's slower to access from 5, 6, 7, 8. Now, whether you expose to the programmer a shared address space or not, that's a different thing, right? So I could be implementing the software layer in a way that I actually fetch data X from the other card by making a send and receive message passing call. Or I can say that I will implement that right at a lower level, and the programmer gets to see a shared address space. So program code is running on card 1 or card 2. It can run on any of these cores. It always sees X in the same way. That can be implemented in software. Even though underlying messages are getting sent over this AMD hypertransport, if you take Intel quick path, these are all networks, right? Off chip communication. It can use hardware to actually send, receive messages and take X from here and put it on this memory. But I may expose it to the programmer, or I can build a layer and give it the feel of a shared address space. It depends. Right. So, in a sense, I want to highlight here that, see, having uniform access address space or uniform access or UMA is sounds very good, because if you can build a very systematic kind of layout design, right, where every processor has uniform access to every piece of memory, it looks very regular architecture, and costs are very easy to estimate, right? When you do performance tuning, it's pretty easy to kind of understand how to do this. However, the problem is often uh, is the scalability, right? So suppose what happens is, let's take the example of an SMP machine. Let's take this, right? So let's say your memory controller is getting bottlenecked, right? Now, if somehow you're bringing a lot of memory accesses from all the cores, it becomes bad and creates a bottleneck here. Like we have studied all these bottlenecks in the previous class, right? Latency, bandwidth. So it will be uniformly bad for everybody. So SMP machines are good when some certain program structures are very regular, but many workloads are not that regular. So you're running a task on core 1 and another task on core 2. Both will get bad performance because they're accessing memory in the same way. So sometimes regular is nice, but uh, it depends. A software and the workloads are very symmetric in nature. So if you're not getting good performance, it will be bad for everybody, right? So that's not a good thing. So costs are uniform, but it's uniformly bad in case its memory is uniformly far away or bottlenecked for everybody. So that's why newer designs are more scalable, because you have a concept of a local memory, some memory that is closer to you, which will have low latency, high bandwidth, and some memories farther from you. So if workloads have some kind of locality of reference, let's say you always access from some piece of code 10% of the data, then why should I put it in a faraway place? I should bring it local to my processor. So I should do an architecture like this. Let's say code 1, code 2, code 3, code 4 run certain processes of your algorithm. And I want to put data they need in this memory, because I know that there is a lot of locality of reference, and the other data I keep it in somewhere else, right? So it's good to sometimes scale software which are not very regular in data access using a NUMA machine. So these, I'm discussing these because when you write data analytics software, there's a certain systems aspects here, right? At a hardware level, which we will also later discuss in a software level, that sometimes you'd want to have non-uniform access because data is not accessed uniformly. All data is not accessed by everybody. There's always a skew. So understand that workload, and then you may adopt a NUMA architecture. In fact, when you write cluster programs, it's inherently NUMA, because as I said, if you uh, if you replaces interconnection network from a fast on-chip network to just Ethernet, this is nothing but a cluster, right? And most of the work you ever do in data analytics are on clusters, right? So it's basically a NUMA machine, and that's why locality of reference is important, and it's often found in systems, hence it works out quite well. So designs are more scalable, NUMA designs. However, you'll have trouble also in performance tuning. Like you have to find, exploit locality, right? So you have to figure out which accesses are important. How do I make it local to that particular piece of code? So you have to be a good programmer often, right? So cost is often increased for programming effort and performance tuning. I already discussed this shared address space versus shared memory. Often people confuse these two terms, right? Uh, so shared address space is more of a programming abstraction, because you are giving a feel to the programmer that you can access any data, and uh, you don't need to do explicitly some send and receive transfer calls for bringing data from another machine to this machine. However, when you talk about shared memory machines, it is specifically how the physical machine is architected. So you can have a distributed memory machine, not a shared memory, but still build an shared address space on top, because you build the message passing layer and the programmer does not see that under the covers messages are getting exchanged to move data from machine 1 to machine 2 when some program running on machine 2 needs that data. Okay, so understand difference between these two terms. So it is possible to provide a shared address space using a physically distributed memory. So even if I have this kind of an architecture, I can always give the feel to the program that look, you don't have to move around data using send and receive. My software layer takes care of it. So that's why you're giving it a feeling of a shared address space. Okay. So shared address space, again, just to repeat, Pratik, uh, shared address space is when you run some piece of code here on the first processor, right? And it's actually residing on the data is residing on the second processor here. But you as a programmer don't need to write message calls to take this piece of data and move it to this memory for this processor to access. There's a layer built on top where all these memory pieces are kind of put together at a software layer so that you access anything, it goes through that software which will fetch data transparently. So you are given a feel that all this memory is one. It's one big piece of memory across machines. That's a shared address space. Can be done in hardware, can be done in software. When you go for this kind of an architecture, it's already done in hardware because there is no other way you can do it. Every processor can access any memory, right? In UMA machines, these are anyway shared address space is taken for granted. Why would you pass messages? Yeah, you can think of it as an index to all machines' memories. I mean, how do you do from a processor? How do you access memory even on your computer, right? It's an address. You put an address on the bus, and that goes and fetches data from the memory bank. You don't say in your program, "Oh, my data is on memory bank one," and then you fetch it from there, or data from memory bank two, right? The operating system hides all that complexity for you, right? In fact, the memory controller hides all that complexity for you, right? Now think of the memory controller hiding all that complexity from you here, right? When there are different processors, like actually on your laptop, there are multiple cores. All the cores access all this memory banks. It's already shared address space and shared memory. But now think of that. What if there were two laptops communicating over an interconnection network? Suppose this, I had two cards and they're kind of communicating over this Intel quick path, or if AMD's hypertransport something. Now in software, you have to provide this abstraction layer, right? Because there is no central memory controller which will hide all this complexity. There are two memory controllers, right? Okay, so let's take some summary examples to end this discussion on different types of parallel computing hardware you might encounter. So if you look at the left side diagram, this of course doesn't exist today because your mobile phones are also multi-core. So think of the core containing instruction unit, functional units, registers, is a one cache, there's a two cache, this is memory, right? Single core computer. Then you start doing some sort of parallel processing on multi-core machines. This is what your laptop looks like today, right? That you have two cores, each of them kind of replicated the function with their own L1 caches. That's a shared L2 cache, goes to main memory. This is a shared memory machine. And of course, because it's all memory is anyway physically centralized, you will have a shared address space as well. So when you write a multi-threaded code, which we will cover in the next session, each code is probably running a thread, right? And they're both accessing same memory, same address space. Now, if you push it a little further, if you go on the left-hand side, most modern codes will have hardware level multi-threading, right? So this core, because there's enough number of transistors on the chip, will have multiple instruction units, multiple functional units. So that's what is called multi-core hyperthreading. Just extending the previous one to say I'll have multiple instructions I can run together on a core, right? So most of the multi-threading is done at a hardware level itself. Now you can expand that thought even further, which if you look at the modern GPU architectures, GPU were originally graphics processing units used on for mainly your graphics cards. And over the last several years, GPUs have become very popular because when you want to build a massive multi-core machine, it's best to use a GPU architecture compared to a regular general purpose CPU core. So here it may be hundreds of cores, right? Not just a couple of them or 8 of them or 16 of them, but hundreds of them you can put together with some local memory, because this is your what your graphics card used to look like is exactly this. I mean, if you have in a gaming kind of a person, or if you're doing graphic design, you'd always get a separate graphics card and plug it into your motherboard, right? Basically, it used to look like this: a lot of memory and a lot of cores, so that you can get a lot of parallelism on embarrassingly parallel tasks. For example, in gaming, why would you use this? Because let's say you're playing a game, you're rendering a 3D scene, right, in 2D on your monitor. That's basically what is done polygon rendering. There's a graphics pipeline that does it. It's basically splitting up your uh, uh, data into small chunks, and each of them independently kind of going through a rendering pipeline. So it's embarrassingly parallel. There is no data exchange required between the different segments. So people used to use for graphics processing GPU cores. But nowadays, these modern applications for AI, machine learning, they also have some sort of behavior like that, where they can partition data and independently run them on multiple cores to speed things up. That's why GPUs are getting adopted. So when you look at a lot of parallel computing use cases, they will involve this GPU system. It's often called the GPU accelerator, right? Which is basically saying you have this general purpose CPU cores, but if you want specialized tasks to be done, either graphics or AI applications, you can run them here, right? So you offload here and get the work done into CPU memory, and then give it to the CPU cores for displaying to the end user. So a lot of data processing happens on the GPU side. This is your gradual progression into like really parallel systems, right? Now you can also get a hybrid architecture like this, where you basically put a bunch of cores with shared memory, and then you tie them together into some kind of backend network. Now this backend network could be very expensive, right? Where so then it'll start looking like sort of this, right? So what I could have done, so imagine this one box here, there are two boxes, right? One of them, this is a shared memory system. I've put two shared memory systems together, right, to communicate. So this is something similar, right? This is one shared memory system, another shared memory system. I've connected them together through a backend network. And then there could be a front end node which will be kind of pushing different workloads to these machines. So it's kind of a hybrid, that there is distributed memory across all these backend nodes connected through some network where you can move around data through messages. And you have also shared memory on the same machine. This is how modern clusters look. All clusters are like this. They're multi-core machines exploiting shared memory. So you can write a multi-threaded program. So let's put our programming in context now. So when you're writing core on one machine, you will write a multi-threaded code. At this level, you will write multi-threaded code on one box. So you will use OpenMPI or pthreads and all this to kind of write this code. Whereas when you run this code across this machine at this level, you have to write some kind of a multi-process code, right? This is where we will get into OpenMPI coding. This is where we will get into OpenMP or pthreads library. You can have Java threads also. There are many threading technologies. So you could use these kind of libraries to code. So just to put this in perspective. So most applications you will build will have a piece where you break up different tasks into different processes and put them on different nodes in the cluster or different backend nodes using OpenMPI or some other library, right? That passes messages. because you have to move data from one piece of memory to the other, right? And then if you are trying to speed up the code running or the process running on one of these backend nodes, you will write multi-threaded code. And there are many technologies for that as well. So most of the cluster programming you will do is basically hybrid. And then on top of that, if you look at the lower diagram, each of these backend nodes could have a GPU accelerator, which means now you have to not just use this OpenMP and all that, you have to enhance it further. You have to say, let me also understand plus, let me also get into GPU programming libraries, right? So people learn something which we'll not do in this course. People learn something like CUDA. CUDA is a library for writing code on top of these multiple cores on a GPU accelerator. It was an NVIDIA library that they open sourced and it's called CUDA now. Okay. I hope this structure is clear. When you write a parallel program, including your assignment, essentially you're writing an OpenMPI or an equivalent program to kind of run multiple processes across different nodes and who don't share memory and exchanging messages between them. But each of those processes have to be sped up using some sort of multi-threading because each node in the cluster is multi-core machine. And on top of that, you may have to learn some GPU library to actually exploit not just the general purpose cores, but the GPU cores on the machine. If there is such a machine that you have either taken locally or on an AWS or Azure cluster, right? It depends what kind of workload you're running. Okay. Uh, Question is one GPU is better than the other. Uh, we won't get into that discussion here. I mean, whether I don't know if you mean by whether a certain GPU processor is better than the other processor. Same question as saying I can take two different general purpose cores and how do I compare them? How do I know Intel i7 is better than an AMD equivalent? Right? That depends on many, many things. And that's not a scope of discussion here. Why is one GPU better than the other? Okay, but I hope this conceptual structure is clear because this, when you get to the assignment, I will explicitly tell you use OpenMPI to write a multi-process program. Now, multi-process program can also be written on the same machine because what will happen is, see, your machine, single machine anyway gives you virtual memory. So when you run two processes, they actually have their own address spaces. So even though, so let's say you only have one machine, you don't have a cluster, you're writing your parallel program on one machine. If you write a multi-process program, even though you have shared memory, your operating system anyway is giving you different address spaces. I run process one, it uses part of the memory. I run process two, it will use part of the same physical memory, but it will have its own address space, right? So I'm simulating two different address spaces on the same machine because my operating system virtualizes at a process level. So in your assignment, you can always run a multi-process program on your laptop because you will get some parallelism because there are multiple cores. So you can always run two, three, four processes and you will get some parallelism, better performance. But you will not use shared memory because you have already created multiple processes. I hope that is clear. If you wrote a multi-threaded program, actually you'll be using the shared address space. But if you run two processes, they have their own address spaces. That's basics of any operating system, right? You must have taken those courses. So in the assignment, you are free to run on one machine, but you have to show me how you write a multi-process program. And when you write a multi-process program, you have to explicitly move data around. You cannot uh, avoid that, right? Because process one does not know the data that is lying in process two. So I will not tell you in that assignment to use multi-threading. Uh, you could do it for your own experimentation. That means that when I run two processes, if process one or process two individually I want to make faster, I can write a multi-threaded program, but I will not ask you to do that. And definitely I will not get into GPU clusters because you may not get access to such a machine. Okay, very, let's do a quick discussion on the remaining, so about interconnection networks. Uh, I talked about some of these already, but let's give you some types, right? So this is, so typically what happens in a, there are two types of networks, interconnection networks, because one of you asked that question. I think I did not cover it in the previous class. I'm sorry. So this is, these slides were for this class where we talk about what's a cross point switch and so on. So two types of interconnection networks you can think of. You can classify it as a static network where all these nodes are wired together in a certain way. That means there is no switching. You have directly connected, saying that this process can only talk to this process. So this process, let's say P1, this process, let's say P1, cannot talk to this process P2 directly because there's no wire between them, right? This is a static network you have built. Now, whereas if you use an indirect network or a dynamic network, that means you're actually putting switching elements, and depend on the position of the switching elements, you can talk to any process, right? You don't need a direct link between them. That's why the switching element comes in. Now, it is possible in many very custom built supercomputers, they will actually use a static network because it's built for certain kind of, let's say, matrix manipulation operations and so on. So they will put certain topology in place among between processors with no switches. Whereas most machines you will deal with will have a switching network where anybody can connect to anybody. It depends on how efficiently, depends on how your switching network is built. So let me jump to some slides and show you that. Think of now when you build a switching network, these were the extremes I was talking about. Not extremes, I mean, this is one extreme where I have a cross point switch. This means that any processor can talk to any memory by just clicking on one switch. And parallelly, any processor and any memory can talk, right? Whereas this is something that is more of a using a little bit cheaper uh, switching network, where if I go from one processor to another memory, it's not a direct connection by one switch. You can go through multiple switches. In this case, you have to go through two switches, but it's cheaper because see here, for four processors to talk to four memory banks, I need 4 cross 4 equal to 16 switches. You see there are 16 dots here, 16 switches. What about here in the second case? Second case, I just have 4 switches. There are 4 boxes here. So definitely my cost is lower. What do I sacrifice? I have to go through these 2 hops or 3 hops. To connect this processor to this memory, I have to go through these 3 hops. So my latency is higher, right? But this is a 2 layer or 2 cross 2 switch topology where I use 4 switches. I reduce cost to 1/4, but I triple my latency. So now it depends on how expensive a machine you want to build. You can go for this left side, or you can go for this, or you can go even simpler. You can say, I just have a single bus. I have just one switch. Bus is nothing like a, it's like a one switch, right? Where if one guy is connected, the other guy cannot connect. So most of your laptops, commodity hardware will have buses. More expensive machines will have this kind of switches. Very expensive machines will have cross point switches where they absolutely to reduce latency. Okay. So switches are nothing but kind of fixed number of inputs. You basically connect inputs to outputs, right? It's a map. Some simple definitions you can go through. So as you increase degree of a switch, which means how many ports do you have, of course your cost is going to increase. Think of an Ethernet switch, right? So the number of ports you have the switch, the cost goes square because you have to connect one port to the other, right? So order of magnitude is square. So these are some examples If you look at your computer, the memory bus, IO bus, these are all buses, typically not switches, right, to keep costs low, and they go to a network interface, and network interface typically is a switching network. Uh, Typically, what will happen is uh, when you build these topologies, it's a trade-off between performance and cost, right? So commercial machines will implement some hybrids of different kinds of topologies. Now, if you look at a network interface, it depends on how you connect the network. In most machines, uh, the processors talk to the network via the network interface, right? Because you're sending, receiving messages. Now, your network interface may be connected to the memory bus or to the IO bus. Now, it depends again on the cost. Memory bus is definitely more expensive than the IO bus. You must have learned this in computer architecture courses, right? Memory bus, memory speed is higher, so it has to be more expensive. And IO bus technologies are cheaper because they are typically connected to peripherals, to storage, and so on. Now, if I'm connecting my network to my memory bus, that means I want very fast connection to move data from one processor to another processor. So, but hanging something off a memory bus means it's more expensive. It's like if you build a highway, there is an express lane. So memory is an express lane, and this is a slower lane. Do you want to talk to the express lane? Of course, cost is higher, right? So if I build a machine which is, let's think of, let me go back to this diagram, right? Now I could be connecting these two through a memory bus. In that case, cost will be more. Okay. So yeah, so this is with a memory and IO bus. I said memory bus is more expensive. Now, if you look at buses, I mean, we already talked about it. A shared bus is typically a major bottleneck. So if you want to do a bus, that means you want to keep costs low. And if you want to build a switch, right? Of course, depends on how many degrees and of the switch and all that, it will be more and more expensive. Bus distance between one node to the other is just order one, but then you have to get access, right? Uh, Maybe you have a high latency. So once you get access, you can move data immediately. But if you don't have access, you have to wait. So let's look at the last topic because that will lead us to studying OpenMPI next as a message passing library that you can use for programming. We have talked about a bunch of this, but this is a recap of, again, what would you do in shared memory systems and what would you do in distributed memory systems. So most of the message passing platforms, which means most of the newer machines where you may use memory message passing, these comprise of a set of processors with their own exclusive memory, their local memory, right? So if you look at it, most of the clustered workstations, they have their own memory, but you want to access data sitting on another node in the cluster. So these are non-shared address space. You don't have a common address space. We talked about this already. So which means now you have to program using send and receive primitives. Now you can use TCP/IP stack, right? If you know network programming, you can of course send and receive messages on TCP, UDP. If you have taken a networking course or done socket programming, you know you can send and receive messages. However, uh, it is very laborious to actually understand TCP/IP stack because if you have a different transport protocol, a different network under the covers, not the same exactly TCP/IP, or you want a little bit better semantics, like I want to broadcast a message from one node to all the other nodes. You write a lot of code. So often there are libraries built on top of TCP/IP and UDP, and these are libraries called MPI, PVM, which is a parallel virtual machine. These are libraries provided on top of your networking stack so that programming becomes simple for you. You don't have to write a send and receive call in TCP/IP or socket. There's a higher level library for sending and receiving messages, and then they give you a lot of functions. So we'll talk about those functions. So it needs little hardware support other than a network. right? And as I kept saying earlier, shared address space platforms can also emulate message passing. Reverse is of course more difficult to do, right? So you can make a shared address space, what looks like a shared address space, you can always send and receive messages there. Or if you are doing send and receive message passing, you can build a shared address space platform on top, right? It's always possible. But if you have a distributed memory and message passing, to build a shared address space abstraction on top is more difficult. So just to give you an example, it's like saying that uh, I can have two threads, which is shared memory programming, right? Shared memory address. Exchange, I can have two threads exchange messages. That's trivial. I can always do that. On the same machine, I run two threads and I can always do a send and receive between them, right? But reverse is very difficult to do, right? If I have a system which actually can exchange messages, like two processes on two machines exchange messages, but now you want to somehow abstract on top that these two processes can access a shared variable magically and you under the cover exchange messages, of course that's more difficult to build, right? So let's look at different memory access models. Again, this is fairly simple. I think we've gone through most of the discussion. So when you look at shared memory, what you are doing is there are multiple processes, multiple pieces of code running on these processes, and then you are accessing the same shared memory physically as well as in software in the address space. Distributed memory means that every processor has its own local memory and you have to send the packet or the message from one to the other to copy data. Otherwise, one processor cannot magically read data sitting in another processor unless somebody transfers this data. So think of processor P1 having memory 1, processor P2 having memory 2. You have to copy this data from memory 1 to memory 2 when processor 2 needs something in memory 1. You have to copy that particular piece here, right? So I think this we have already gone through. I'll skip. Essentially, this is this. I mean, so many slides just say the same thing, that I have data item X sitting on process 1. It's a local variable X, and I have to do a send call across the network. The data will arrive at process 2, and the process 2 will copy this data into some variable Y local. I mean, you can call it X also, but I kept it X and Y because these are different addresses. These are different. This is different memory altogether, right? You copied the same value here, but the address location is different on different machine. So then the program running on process 2 can access this particular Y. So that means these guys have to coordinate somehow. So all these message passing libraries that we'll use will do all this coordination. So think of an example here, and this is very similar to the assignment that I will give you, which you will implement in OpenMPI. So what will happen is the following. Imagine that there are three processes. You can think of these as three processors, three nodes, anything, right? Let's say I give you a bunch of data. I give you a million employee records. You have to process those million employee records. Maybe you have to find out what is the maximum salary of an employee, right? Given a certain role, let's say an employee who is a software engineer of level something, what is the maximum salary among all the instances? And I give you a million records. Now this can be done in a parallel fashion. I could partition this data. Let's say break up this data into three chunks. I give some chunk called data item X here to processor A, the second chunk to processor B, the third chunk to processor C. So first I have to partition them. Then each of them do their own operations. Let's say their own, one third of a million records are sent to this, right? Each of them do their own processing the final result they have to somehow send to one of the processors, because the user wants to know the final result, not like three independent results. So now when the data, process data, which is let's say x prime, y prime, z prime, this is the processed output. So in this case, it could be the max. So I went through 1/3 of a million records in processor A and I found the max in it. Similarly, processor B found the max in its own data set. Processor C found the max in its own data set. So now these three maxes, X prime, Y prime, Z prime, of maximum employee salary, who is a software engineer of level 7, let's say, is sent to processor A, like one of the processors you can decide, right? And then A will actually go through this, do its own processing, maybe take a max of these three and output the value. That's my good result, right? That's a max of everybody because I did three maxes and a max of the max. It's still a max. So I got employee number 7 here, employee number 100 here, employee number 1 millionth here, right? As the maxes. And then I did a comparison among them and I got who is the highest paid software developer, right? And I give the result back to the user. I did parallel processing, but I'm moving around data, right? I partitioned data and I put it on 3 nodes and I got the results into one of the nodes and I gave the answer to the user. So see, there is complicated programming in sending and receiving messages across machines in the cluster or across processes, but this complication is only in one or two phases. Like I have to partition the data. That's where a complication is. Like how do I partition it? Which data do I put where? I have multiple considerations there. And then when I'm done with the independent processing, I have to merge and collect all this data in one place, maybe do some finishing processing, and then give it to the user, right? So uh, looks like not a big task, right? Only thing you have to learn how to send, receive messages, and how to partition data and how to merge outputs and so on. It's a nice way to parallel process. Now, when we study Hadoop later, Hadoop MapReduce, uh, you will appreciate that later. I'll try to put together a webinar for that as well, besides having one class on Hadoop. You will realize that when you do your first assignment, you will go through the pain of moving data across processes and doing this job. But when you study some higher level middleware like Hadoop and Spark and so on, some of that moving around work is done automatically so that you focus on the processing. So what was the processing I was doing in my example here? I was calculating max. Now I can do more complicated calculations, but here I'm calculating max. Now, instead of focusing on how do I calculate max of a bunch of numbers, I also have to focus on how do I move data. What Hadoop, Spark, all these different technology stacks do for you is they will do under the covers all this hard work of moving around data in an optimal fashion, whereas you just focus on writing the max function or any other complicated function. So that's what Hadoop MapReduce programming is, and we will talk about that later. But I think a good thing is for your first assignment to understand the underlying principles and how you write it yourself using at least a message passing library. Then you will appreciate that when you get to know an analytics platform like a Hadoop or a Spark, how much easier your job becomes, where you focus on the analytics function only, but not the distributed execution that the cluster takes care of. Okay. So the assignment I will give you will be very similar like this. I'll give you a data set, you have to partition it, you have to get the work done parallelly using OpenMPI. So I'll give you the library which will move around, which you can use to move around this data. Okay, these are optional charts, not too important. Okay, this was talking about synchronous execution of task is difficult to achieve given the environment. Yeah, so on the other, asynchronous execution is what you should typically do, but it's hard to reason. So you must have encountered this earlier also. Like when I parallelize something, let's take this example. Let's say this is running as 3 parallel processes on ABC, right? processing data item X, Y, and Z. Uh, Now, these could be run synchronously in lockstep fashion. Means when A is doing its work, B is exactly at that point of time doing its work, and they all finish together and then combine. Or it could be asynchronous. I could be just executing A because A is a, let's say, a better machine. So A does its work faster, but B is slow and B takes a lot longer time. But asynchronous execution means I don't have to wait for everybody, right? I can ask it to start and it can keep going. I can do something else. So you will realize that synchronous execution of tasks is difficult. It's easy to reason with because I know how things are working across different parallel tasks. But asynchronous is more efficient because you don't need to wait for the slowest person all the time. You can keep going. But it's hard to reason with, which means when problems happen, you're dealing with a very complex system where things are starting and stopping at different points in time, right? So proving certain properties like how much have I progressed in my program is difficult to understand. So we'll see some of this even in the send and receive calls. There are synchronous variants, there are asynchronous variants. So let's take an example. So let's say you do message passing, right? So let me take an example from MPI here. So let's say there's a sender S and a receiver R. So I'm sending data at a certain point of time from my program. This is where the MPI send function is called. There's a variant called synchronous blocking send, S send. So data here, if you see these dotted lines, data is getting copied from the user level program into the operating system kernels and it's getting buffered there. And then data starts going out on the wire, on the physical medium, right? And the last packet goes out here. The task waits till that long. On the receiver side, what happens is, let's say I make a call here, but the data starts coming in later. So I make a call exactly here. See where the arrow is, MPI receive. Let's say I make the MPI receive call somewhere here on my receiver side program. Now the receiver has to wait till all the data has come in, right? So this is also a blocking call. That means on the receiver, I'm blocking to get the entire data. So I have other work to do, but I'm not doing that. I'm waiting for the data to come in. It's a blocking call. So this is the most inefficient way, but it's a very fault tolerant way because if something goes wrong, the sender and the receiver immediately know. Not like later that, oh, I sent data but did not go through. Or by the way, I made a receive call, but ultimately data did not come in. So you are getting better kind of error handling here, or you exactly know when data failed, right? However, you are unnecessarily waiting and making your process slow, which means you're not executing enough parallelly. So your efficiency goes down. So there are alternatives that exist. So there are mechanisms where in a send, you can do asynchronous and blocking. Asynchronous means I can return whenever the data is copied. So think of this. My synchronous send is it's waiting till the data is actually going out, whereas a asynchronous send can be that right here, when I've copied the last bit of data somewhere here, right, in the dotted line, somewhere here, if I've copied the data into the kernel, into the operating system, I can return from there. I'm not waiting for the last bit of data actually to be sent from the buffer on the network card to the hardware, the link. So that improves my parallel processing. So I've given a link at the bottom of this chart. You can go read this article where I've taken this from. And I will not go through all of these in depth. I give it to you to read, but essentially you will see variations where I can actually not wait for the entire thing, but return intermediate steps so that I get more efficiency out of the system. Only thing is I have to keep checking that did actually data get sent out or did actually data get received, right? So there could be asynchronous and non-blocking options. So we'll look at some examples later, but just check on the paper, and if you have taken a networking course, any kind of socket programming, you will see these options anyway in most send receive calls. So look at the receive side. Receive side non-blocking essentially means that I make a call to get data. However, data has not come in yet, so I can immediately return, and I can check later about the status. So think of this diagram here. I made a call here, but I'm waiting. So these dotted lines here, the big dotted, the dashed line, this part can disappear, right? I can make a receive call, nothing is there. I come back and keep doing my work, and I set a status so that I can check that status very light way, or I can even sometimes I can get libraries which will send me a trigger when data starts coming in. So I get more parallelism. I don't need to wait. Okay, so efficient ways are there, efficient options are there when you have non-blocking or asynchronous sends and receives. There is a big advantage of using those also. When I go to OpenMPI, I will show you different advantages of using asynchronous. Not just improving efficiency, but it helps you in other ways when writing a parallel program, like resolving deadlocks. So we'll come to that. Okay, so let me switch from here into the other deck, because then we'll start getting into specifics of how you do the send and receive. Now, let's see. I'm thinking, let me start with OpenMPI. There's a bunch of different kinds of primitives. Let me come to that later. That's a little bit of more theory, right? So I will cover that later. I'll skip through some slides, which will again come back in the next session, but I want to cover certain pieces in the programming so that you can get started. And then variations, theory part, we can keep talking about. Uh, so I'll skip through a few slides here. And those will be taken up again in the next class as more like a revision and some background theory. So what is a send and receive? I mean, those of you have not taken networking course, never written a program using send and receive functions, for them, this is a good thing to understand. So any library that you encounter will give you a send and receive call, which is of like this format. You will have some kind of a, and these examples are using C-like syntax, but you will find similar thing in other languages. You can use any language you want. Uh, so you will have some buffer to send, right? So this is a send buffer. The star is a pointer. In C, use a pointer to point to a memory location. So send buffer is an array or a memory location. You want to send data from there. You want to tell how many elements I want to send out, right, from this buffer, and which destination should I send it to. That's a typical send call. On the receive side, your typical syntax is of any libraries. Here is my buffer where you should be receiving the data, and you should be putting it here in this memory. I want to receive so many elements, and I want to receive it from this particular source. Now I'll show you calls in OpenMPI where you can say I can receive it from any source, but this is kind of a generic prototype, right? It's saying that there could be a parameter which exactly specifies which source I want to get data from or which destination to send data to. So you typically have these three parameters and maybe sometimes more, depends on the specific library. Now, if you look at this program segment, there's a processor P0 on the left hand side and a processor P1 on the right side. There are two processes running on two different processors. So let's say, so variable A is equal to 100. This process sends this location of this memory location of variable. Ampersand A is a way to write in C that I want to send out data sitting in this memory location. I want to send out only one element and I want to send it to a process one, which is P1. And then immediately after that sending, I assign A is equal to 0. Simple sequence of steps. What happens in P1 is I want to receive this. I want to call this A here. I could have named it B also, not an issue. And for clarity, I could always write this as B because this is a different memory location on a different process. Even if we call it A, it's actually a different memory location anyway. I want to receive one item and I want to receive it from some process ID 0, which means this P0, and I want to print it. Simple, right? Now, the semantics of send operation should be such that when I receive and print this, the value should be 100 and not 0. It should not be that as I'm changing this value from 100 to 0, the send is also working and somehow send happens later and it picks up this value 0. That's wrong, right? I didn't mean that. This is where you have to be careful when writing programs, especially if you use asynchronous versions, asynchronous non-blocking, because the send, basically what may happen is by the time the send is got grabbed already a value changed, right? But in the program, you did not mean that, right? You meant to send 100. So when you look at libraries, there are lots of options in doing sends and receive using asynchronous, non-blocking, running send in a very non-atomic fashion. Ideally, it should not happen that if you meant to send 100, you should not end up sending 0 because memory location changed by the time send went through. Okay. Uh, Let me skip these because I'll talk about these in the next class about different types of buffering. We come to discussing open MPI first because then we get a concrete example and then we can go back and study some of the different options that could have been possible in synchronous, asynchronous, and so on. Now, in the message passing model, typically what will happen is you'll have a process. Pratik, I'll come to non-blocking in the next class again. So don't worry about it now. I just introduced to you asynchronous non-blocking, but we'll come to those later because I want to get through OpenMPI so that you start writing some code. I'll share some code today and you go through it. You understand the basics and then we'll discuss options, uh, more the theory part and different options next session. Now, uh, basically a process will have a program counter and some address space, right? When you run two processes, there are two different address spaces, even though you're running on the same machine. And processes may have multiple threads. So this is where multi-threaded programming comes in, right? So you can have multiple program counters and associated stacks. So when I teach you multi-threaded and OpenMP as one of the examples of creating multi-threaded programs, then you will see that I can take one of my processes and I can actually make it multi-threaded to further kind of make my process faster. But that is sharing a single address space. So MPI is for communication among processes. It's not, don't use it for among threads because processes have different address spaces. Now, when you do inter-process communication, basically synchronization is one thing that you have to be careful about between these processes and then the movement of data, right? That's what we are primarily focusing on now. How do I move data from one process to other using sends and receives? So there are a couple of ways that are there. You will typically use this method, not the second method I'll talk about. This is called cooperative operations for communication. This basically means that when I send data, the other side has to also call a receive, right? Or when I call a receive, somebody should have sent data to me. Like in the small code snippet I showed you earlier, I transferred A and the other guy got A and put it in B. I called send and receive. So unless I call a send, the other guy will not get the data. So basically this needs the receiver's explicit participation. So they have to cooperate. So OpenMPI version 1 onwards, or MPI is a specification and OpenMPI is a open source implementation of it. There are multiple MPI implementations by different vendors. OpenMPI is an open source one. And will use OpenMPI. Now, MPI version 1 onward supports this, send and receive. There's an alternate also possible, an MPI version 2 onward supports that, which is called one-sided operations, where processes don't have to cooperate. So if I want to send data to a second process, I can make a call like a put data. It's like saying that I don't need your permission to put data in your memory. Similarly, If I want to get data from you, I can make a call and data will be fetched automatically. So there's no explicit send and receive. Now, the advantage of this kind of communication is I have decoupled the communication from the synchronization, which essentially means, look at this, sender and receiver have to synchronize. When I send data, there has to be somebody on the other side to receive. So the mechanism of communication is coupled with synchronization of the two processes. So when I discuss the next session, some of the uh, theory part of different options of sends and receives, which are these diagrams that I will go through, not right now, you will realize that a lot of coordination is required. However, here no coordination is required. So if I want to communicate without synchronization, I can do that, right? So when you want to decouple them, you can do it this way. When there are use cases where you want synchronization also, you do send and receive. So most of your programs, I will focus on send and receive when you write code. We will not get into this, but you know that the option exists. Okay, so let's go into some OpenMPI programs. Let me see how much of information is here. So we should be able to cover this today. Yeah. Okay, so what is MPI? It's basically a library specification. As I said, there are multiple implementations. Different vendors will have their own implementations. OpenMPI is what you will use for writing your programs because it's free. It's open, downloadable, free. But when you buy different cluster kind of hardware from different vendors, they can give you their own OpenMPI spec also, because not OpenMPI, the MPI implementation, because they claim to have done some optimizations to make it faster and so on, hardware specific optimizations. So this is a specification to essentially extend it's an extended message passing model. I mean, you could have used a TCP IP socket programming, but this is a more extended. It has more kind of options for you to do this communication between different processes. It is not a language or a compiler specification, right? It is also not a specific implementation. OpenMPI is a specific implementation. So MPI is a standard. So essentially, if you want to do parallel programming on different types of hardware, uh, you can do that without knowing details about that hardware, right? So if you are a library developer, a tool developer, you adopt MPI to implement some of your code. End users gain why? Because you don't have to be conscious about what the exact hardware is to do this, because OpenMPI or MPI spec, whoever is implemented, will do all that handling for you. Now, having said that, again, let me remind you that when you study some of the Hadoop, Spark, this kind of programming, distributed programming platforms later, you will realize that there is even a higher level abstraction where you don't even have to make send receive calls, right? You just have to write your analytics code. So why use OpenMPI? Because it's pretty powerful, efficient, portable. This is very important, portable, right? And it's basically explicitly done to enable libraries. So when OpenMPI is library, which is a specific implementation of OpenMPI. So OpenMPI is let me write that down here. OpenMPI is a library that implements MPI spec. So when you enable a library, that means you have enabled somebody to build OpenMPI. And similarly, let's say somebody has Sun or some Oracle, they implemented their own, for example. So it's a message passing interface, standard library for message passing that can use C, Fortran, define syntax. So now this is a very important statement. I'll show you which ones, but basically if you want to get started, all what you need to know is 6 method calls or 6 routines to get started. Now here it says C or Fortran, but then you can do in other languages also now. I'll give you some pointers. You can also look it up. You can do Python, Java as well. But as long as you know 6 of these functions, good enough to start writing programs. So we'll go through the 6 functions today to get you started. So here are your 6 minimal set of routines. There are many other routines, but 6 is good enough for you to get started writing some code. So you have some init which will sort of do the initialization. In the beginning of the program, you have to call some init. There is a finalize, which is kind of the last step to kind of close down your program and terminate it. There is something called an MPI com size. So as a process, let's say you want to understand how many processes are there in the overall parallel program now. Because let's say I, as a user, started the program with 100 processes. Now, each of the process code may want to know how many are there because they don't know. I mean, somebody started the program on 100 processors, but the code wants to know currently how many are running. What is the number of processes? So if I have started with size 100, then this MPI com size, if you call this function, then it will tell you that there are 100 processes running. Why is it important? Because based on that, some process may decide to send messages to all these 100 processes, or it may do some kind of calculation to say, okay, looks like I can give 1/100th of the data I have to each of the other processors, right? So I can do many things with this size number. What is rank? So if I have 100 processes running, every one of the processes is given a label like 1 to 100. So when I make a call, MPI com rank, each process, when they make that call, they will get a unique number, which is their rank. So they know what is their ID. This is not a process ID as in an operating system sense. This is MPI's process identifier. So when I can send or receive, I can use these process identifiers. So I can send to process ID 99, or I can receive from process ID 20. And I know that my own process ID is 5 because my rank is 5. Rank is nothing but your own process's ID. So, and then send and receive are, we went through some simple prototype earlier, right? So every message passing library will have a send and a receive function. And there'll be variations of that we'll go through later, but basic send and receive. So let's go through what these functions are, and I will show you a sample program. I'll share that code also on Canvas with the slides. Slides are already there. I'll share the program after the call. You should at least use the OpenMPI library. I've mentioned somewhere where you download it from, and then you can simply run the sample code and get familiar. So MPI init, as I said, is called prior to any call to other MPI routines. It's basically initialize, finalize. We know that it's for ending of a computation. Basically, it's kind of cleanup. So it kind of makes sure that all the processes are cleaned up and uh, all the memory deallocated, and it's a kind of shutdown for the whole system, right? So you will always have these two functions you will always write. Uh, MPI init also does one work. You'll see in the code that in my program, when I pass in command line arguments, they all will be used to kind of in the MPI init to set certain internal parameters. Now, any of these routines when I call will return. All these routines, data types, constants, anything you do in this MPI code and MPI library will be prefixed with MPI underscore. So you know it's a MPI library defined either function or data type or a constant. And whenever a call to any of these successfully comes back, it'll have this code MPI success, or else you'll get some other code like MPI error or something. So check for this code to know that the call worked. Now, before I get into this rank and size, let's understand this concept of a communicator. So whenever you run a parallel program using OpenMPI, you are basically setting up some kind of a communication domain, which means this process. Why are you doing OpenMPI? You are going to communicate to others. So who are these others? It may happen that you have a cluster with 100 machines in it. However, you want to set aside a certain set of nodes and create a subdomain. Let's say some set of nodes in the cluster want to only communicate between themselves because Maybe they are the controllers in the cluster. You want to build some software where you have like a certain controller nodes that should always talk to each other, whereas there are other nodes which only want to talk to between themselves. So this is concept of a communication domain where it's a set of processes that are allowed to communicate to each other. So if you are within a communication domain, you can only communicate within the domain. You cannot, but you can belong to multiple domains. So this MPI com is a variable where the domain's information is stored. And you have to use this in the argument for the MPI routines to all message transfers. So if I send a message, I must say not just who is the destination, but what is the communication domain. So that by mistake, you don't send a message to somebody, some process ID, which doesn't actually belong to that group or that subdomain. So this concept of grouping is there. If you have studied networking, uh, multicast networks, right? You know that there could be various groups or any group communication protocol. You could create groups. And if you want to send to all, by default, one communication domain is set up, which is called MPI com world, which means whenever you send, it's basically to all. You can address any process. So all processes by default belong to this MPI com world. But you can choose to set up some sub processes, some subdomains, I'm sorry. Now, having set up a communication domain, I may want to understand what's the size and what is my rank, right, within that domain. So you can actually make these function calls. So you can say within this communication domain com, give me the size of it. So maybe there are 10 processes running in that particular communication domain com, so it will return 10. Or maybe among those 10, I want to know my rank. So your rank will be, let's say, 3, right? So rank of a process is an integer that basically ranges from 0 up to the size minus 1, right? Because it starts numbered from 0 of that communication domain. So rank belongs to a communication domain and size is the size of that whole domain. So if I pass in as com MPI com world, which was mentioned here, that means basically it includes all the processes. So I will not run these pieces of code. I'll run something more complex for you to show how this works. But you could use these pieces of code, copy paste from here and run it and see. This is a hello world kind of a program where you basically, the structure looks like this. This is in C, but you can always use Python or Java. Options are there in OpenMPI now. So you first have to do an init. Maybe I have passed some variables to the main function, so I can do an init with those arguments. Then I want to figure out the size. I want to store it in this variable. I want to know my rank. I want to store it here, and I want to print out, right? All this, that what is the rank and what is the size. And you call MPI finalize and that stops. So this program does nothing but you start up when I run this program and as a command line argument, I could say that I want to run this on as 5 different processes, right? Is one same program. So every program will run and they will print the size 5 because I started this program with size 5. I'll show you how to run the program, but let me put in for now here some sort of a command line. So I could be doing something like this. I could say open MPI run. It's called MPI run. MPI run. I could say minus number of processors 100. 5 here since I said 5. And let's say this program is called hello. I run this, MPI run actually triggers my runtime, the parallel processing runtime for that library. And then it will start off 5 processes with the same piece of code. But each one of them will basically print the overall size. So they will all print the number 5, but their ranks will be different. So run this program and see. So they will actually print 0 to 4. So each process will do one of the prints. So there are 5 processes or 5 instances of this will run. Each process will print hello world and their own rank between 0 to 4 and 5 because the total number of processes running is 5, right? Now that is just to get started and print something independently, but these are your basic send and receive functions. If you want to move around data between these, let's say these 5 processes, so you will notice that they are very similar to the prototype send and receive I mentioned earlier, but few more parameters are there because this is a specific uh, or rather this MPI is a specification, and it puts in its own special parameters because it's a richer library for sending and receiving. So MPI send uh, will have a buffer that it wants to send. It'll have a count to say how many elements to send, just like the generic prototype I had discussed. But it'll also, in addition, say a data type. Because let's say, do I want to send integers or characters or what, right? So I'll give a data type. An MPI has multiple data types. In the next chart, I've shown which destination do you want to send it to. So this is basically the rank of the process that I want to send it to. The communication domain in which this rank belongs, because remember, there could be multiple communication domains. By default, you can always send it to all, MPI com world. Also, besides destination, it has something called a tag. This is just some additional filter that you can put in. So let's say there are multiple messages going to the same destination, but you want to send these messages to different parts of your receiver application. So there's a tagging concept in MPI where you can tag the data, and based on that tag, it will be actually sent or received to different destinations. So this additional kind of, besides source test, is an additional tag that you can attach for further level of filtering of data. You can end up using it, or you may kind of put some default here so that tags don't matter. You can like keep a tag all, and so it won't matter. Uh, so as example, there are different data types that you can use. This is a comparison with, if you know C programming language, then this is a comparison with the C data types, pretty much one-to-one mapping, right? It has a couple of extra ones. So these are your data types for sending out or receiving data. Receive is fairly similar. Give the buffer where you want to receive the data, give the count of elements, give the data type of the elements, give the source you want to receive it from, optionally give a tag that you want to filter by the communication domain. Additionally, there is a status. So why is there a status? Because what I could be doing is when I do a receive, I can say that if the data is not yet there, then I just want to return and the status flag I want to check later, right? So I could be doing, so we can discuss some of the advanced send receive calls. You will see the use of status there. Now, if you want to receive data from any source, you can say MPI any source. If you want to have any tag, there is already a MPI any tag pre-built, which means that don't do any tag-based filtering, that anything is accepted, right? So I remember I talked about the status. The status is basically a data structure that you will see where it has information about what happened as part of that receive call. It could be source, tag, some error code, stuff like that can get in. Uh, there are also some associated other functions with the receive, like I can get an MPI get count, which will tell you how many actually data items got received. So I asked for 100, but I got, let's say, 90. So I can use those to also get. So these are a little advanced, so don't use them in the beginning, but you can try them out as you get your basic program running. This let's talk in the next class. I will not go through this now. This is about how do I do uh, asynchronous sends receives, because uh, what may end up happening in certain situations is that when you send data and receive data through across multiple processes, you can end up in a deadlock. In the sense, deadlock means that I can neither send out data successfully nor receive data and complete my process. So all these processes are hung because each one is waiting for the other. So I will go through this in the next class, why this happens. So this will be discussed next class when I go to uh, more advanced topics. These four slides I will omit. I kept them optional for more advanced OpenMPI. I will not discuss here. This will not come in your programming. So ignore these four charts, these charts that are already hidden. I will give it to you, or I think they're already in the deck, but these four ignored. This is more advanced OpenMPI. Uh, this also next class I will cover because I want to skip to where you can get a basic program running. So these next class, uh, okay. Let me get you an example. Let's get that running and then we'll come back to some more advanced features. So I want to give an example which is a little bit more complicated than the hello world that we went through. And let's say I want to parallelize a certain more complex computation, which is like calculation of pi. Now, most of you have taken a math course, may have gone through this, right? That how can an integration operation be done? Or how do I calculate pi as area under a certain curve? So I will not go into the details of what that computation is, but at least just to recap, calculation of pi is basically an integral of a certain function, right? Specifically 4 by 1 plus x square. If I integrate, I will get pi. Now, what is integration? Integration is basically saying, let's take a simple function. This is linear, right? If I take this diagram, integration is nothing but adding up area under the curve, right? And how do I make it more accurate? I should basically get small rectangles, thin rectangles, as thin as possible, and try to kind of approximate area under this curve. So thinner the rectangle, the more accurate the calculation is, because then these triangles don't get kind of omitted from the area. So now what is this, each of these bars? Think of these as intervals, right? So after every uniform interval, I actually want to calculate area of this rectangle. So width of a rectangle is like an interval here. Now, any guess on how I can parallelize this? Anybody can speak up or put on chat, or how do I parallelize this sort of an integration operation? I know you're the code on the left hand side, but can you guess? How do I parallelize this particular integration? Think for a few seconds. And before I get into the code or the mechanism of parallelism, if I give you 4 machines to run an integration function which looks like this, is basically calculating area under the curve, and I have these chunks by which I divide, or intervals by which I divide and create rectangles, how would I parallelize this whole integration operation? Because let's say I create a I create a million intervals like this, right? Million rectangles to approximate, because this integration is, let's say, between 0 and 1, and a million rectangles I create. Yeah, I think Pratik, Akshay, yeah, you're along the right lines. So maybe not each interval, but I would take these, I would break them up into sets of rectangles that are contiguous, or need not be contiguous also, actually. I would break up these rectangles into some way, partition them, put them on different nodes, let them each calculate the rectangles they have, then you get them together and add up. So now let's go back to the diagram that I had shared with you. Yeah, hopefully the screen is refreshing. So I've gone back to the session 3 slide deck where I gave you this problem of employee max salary computation. Doesn't it look very same like this? I have data, which is like this million rectangles. I put 1/3 of the rectangles on processor A, 1/3 on processor B, 1/3 on processor C. All of them do their own rectangle area calculations, add up, send it to processor A. Processor A adds up the 3 results, and there you go. That's my answer. right, of the integration. So the calculation of pi, the only thing is that it's basically uh, a special function that I'm integrating, nothing less, right? So I'm back to the slide titled example calculating pi. If you guys are not seeing it, then let me know. I just changed back to my current slide. So now you're right. So what I'll do in this program is if you follow this code, and this code I will run and show you now. But let me go through the structure of this code. So similarly, why am I going through this is because given any problem, you should be able to think about it that way. Think about a data parallel computation. So what data am I dealing with? In this case, why I'm going through pi is because I've not given you any data. Your data is the function, right? That solves the pi problem. In other cases, I will give you employee data or sales data and chunk it up and partition it and run it like this. But the point is, understand what is my data that I have to break up partition, put it on multiple nodes through some communication primitives like send receive. How do I get that data together back on one machine and output my result? So if you go through this code, what is happening? So first I do an init because I have to, let's say I run this across 4 processors. So I've started 4 processes. So they will all do init. Then I will say my com size is basically this number of processors. So so number of processors is I've defined in my command line. So that is actually 4 or 5, whatever number I put. And so because if I run this with 4 as a number of processes, then what will happen here is num procs variable we will set at 4. Each of those processors or processes rather running, each of those 4 will now get their own rank and store it in my ID. Now I have to somehow determine one guy who is going to output the result because somebody has to collect all this data, right, and put it together. So I designate my ID 0, the process with ID 0 to be sort of the master node. Remember in the previous diagram from the uh, different slide deck, I was showing you processors A, B, C, and they were getting partition data, and all the data ultimately was sent back to A. Think of A being the processor ID 0. So processor ID 0 is responsible for all the user communication because can't be communicating with the 4 processes. So if ID is 0, then you ask the user some questions like how many intervals do you want? So user can say I want 10,000 intervals or 1 million intervals. That's your step size here. Like how do you want to kind of create data samples? Each of these boxes are like data samples, right? Now there is one primitive so these 2 primitives we have not gone through and I'll go through in the next class is broadcast and reduce. Yeah, what if 0 quits? Yeah, so if it crashes, then there's trouble. So you must build fault tolerance at some point, right? We're not getting into all that. MPI is not giving you the fault tolerance. You can build one. So broadcast is nothing but doing like a send to everybody in a loop. So MPI broadcast means that this data is now sent to everybody. So everybody is told what is the size n. That means how many intervals does the user want? And if n is 0, then break because that means user doesn't want to do anything. Now, this data, this overall data, right, is broken up into n chunks by everybody because I'm doing an integration of 0 to 1. So I divide 1 by n to know that what is the width of each of these rectangles. Each of the processes do it now. This is code common to all the processes. Each process is doing this. Each process basically has this value n and it waits till it receives this value n. Moment it receives it, it basically divides this whole uh, interval by n, and this is my incremental kind of h, and then they all do this computation for a certain set of rectangles. Now it could be that if you divide it into 4 processes, everybody takes 1/4, A way to do 1/4 is that you could take each of them, it could take consecutive. So the first, let's say 25% goes to process one, next 25% goes to process two, and so on. That's one way of doing it. The other way of doing it could be that the first process take the first chunk and then the fifth chunk, then the ninth chunk, and so on, right? The ninth rectangle. So first rectangle, then plus four, fifth rectangle, plus four, ninth rectangle. I could go that way also. So either way, it, this computation here in the for loop, you will notice it basically partitions all the data. So me as process ID, let's say 5 or 3, will only look at certain rectangles, because you see this I is equal to I plus num prox, which means the first guy will only take the first, the fifth, the ninth, the 13th, 17th, and so on, right? It will go like that. End of it, whatever rectangles you have, you calculate your own chunk of and store it in MyPy. And then you can send this data back to processor ID 0. Now I have used a fancy function called reduce here. Now, again, next class, I will discuss what reduce is. It's a shortcut for doing this addition where all the data is actually automatically sent to one node and addition done. But you can always say that, let me not use this shortcut. Let me, each of the processes, let them send, call it a send function, and send all this data to process ID 0. And let's process ID 0 receive that data. So you could put code here to say, uh, I could put code here to say if my ID equal to 0, then my ID is equal to 0, then receive data from all processes, right? That could be my code also. But there's a shortcut here given saying that you can do an MPI reduce, a special function which automatically gathers all this data in one of the processes. And if my ID is 0, then only I print the result. Otherwise, you'll get 4 prints if there are 4 processes running. But hopefully from this, you got an idea that you could be taking this data or the function or whatever, doing a partitioning work, independently computing this. Remember, the same code is running in all the processes. And then you do some sends and receive to send data or collect data. And then if designate a certain process ID, which will only execute the piece of code which will output the result. So think about how this works, right? Now, I'll show you the code now, but you download OpenMPI, you can check for 2.0.4 or any later version. You can write your program in C or any other language, see what is supported, and then you can run it. There's an MPI compiler, MPI CC, which can help to compile it. If it's a C program, for Python, it will be different. And then this is how I can execute the same program using 4 processes, right? I use MPI run, minus NP is a special parameter to the runtime to say how many processes you want to run and give it the program name. So now the way you can write your program is, because this is a function I was talking about, I did not input data in a special process and distribute it among others. In your case, what you could be doing in a different example is, I could be saying if my ID equal to 0, then let me read this file from the file system, break it up into 4 chunks, and call 4 sends to send individually the 4 chunks to the 4 processes. That could be special case of my ID equal to 0. Else, if it was my ID equal to 1, 2, or 3, or even my ID equal to 0, because I could be doing processing as well, then receive this code, receive this data, right? And then start working with it. So in the code, make sure you put this ID checks, because the same code that will run across all processes. So if there is a process specific action you want to do, you have to put this check. See here, it was the first process, my ID 0, which wanted to interact with the user to input number intervals or output the data. Hence, I put a check. If you are sending data, I want you to think about this so that you kind of understand how this works. That if you are my ID 0, you could be reading data from the file, your local file system, and then sending it, making a send call, 4 send calls, or rather 3 send calls, because one of them is yourself. You could make 3 send calls to the others. Whereas if you are not my ID 0, so an else can come here, then you call receive. So the way you start rest of your code is after you receive chunks of data from my ID 0, right? And then you do your own computation. And then if you are ID 0, you will wait for others results. But if you are ID 1, 2, or 3, then you have to send the result to process with ID 0, right? And only process with ID 0 will do rest of the computation on all the 4 results and then output it. So I want you to think through the structure rest of the week, right? And we come back and discuss that. But this is kind of a homework for you. Take this calculator of pi example. Think about what would you do in this case. Suppose your assignment looks like this, where somebody, let's say ID 0 process, reads data, partitions it among 3 of the processes through send. So the 3 processes have to call receive. And then these 3 processes work on their chunks and then they do sends. And the ID process, a process with ID 0, actually does a receive from them, does rest of the computation, and then prints a result. See, there are 2 distinct roles here, even though there are 4, even though the 3 processes. There is a master process, process A, which probably does some of the partitioning and distribution, whereas processes B and C actually do only the computation, right? So let me run this code and show you so that you know how to run this when we when you get it on canvas from me. So let me go to my command line. I hope you guys can see the CLI now. Maybe I have to increase the font size here a little bit so that you can read. Hopefully this is good enough. So I will share with you multiple OpenMPI programs like search and a few others, right? You can work with them as examples. But let me open MPI i.c. This is the program that I had given you on the slide. So I'll share this so that you can just copy paste and start trying with it. Again, as I said, reduce and broadcast are shortcuts of sends and receives. But you could think about how to change this program if you did not have these, if you were doing send and receive. But let me run this. So I have, let me see, run it earlier. Yeah. So I'm going to run this using MPI run. I had installed it in my directory, OpenMPI 204. In the bin directory, you will find MPI run. I want to run this using 4 processes. You can say 8, 9. My machine has, I think, 4 cores. So I'm running using 4 so that it works best. You can try using 4, 8, 32 and take some performance measurements also, right? See how fast is it. So I'm running this program. Let's see what happens. So initially it'll ask for number of intervals because remember, first the chunks have to be made, right? How big is your rectangle size? Based on that, the number of rectangles will be calculated and then those rectangles will be distributed across 4 processes. So let me say I want 10,000 to be my number of intervals, which means I have total 10,000 rectangles to be created, which means 4 of them, each of them will get 2,500 each. So let me run this. So it was pretty fast because it's on a 4-core machine, right? So you see each of the processes will calculate their own value of pi because they got 2,500 rectangles, each one of them. And now all these results come back to one of the processes and that process kind of added it up. It's simple addition of these 4 and came up with this number. Now I had already put in the actual value of pi up to a lot of decimal places in the program. So I could calculate the error. Now one can try this and try with 8, 10,000, right? So let me put 20,000 rectangles. You see I have little lesser error, right? So because I have put more intervals, so my, of course, my PAL calculation is more accurate, and it's running across 8 processes. Now potentially I'm running it on my laptop, but if you installed OpenMPI on a cluster, you could be running this across the whole cluster, right? So see how programming becomes simple for me. Of course, I have to write send and receive and broadcast and reduce kind of calls, but I don't have to worry about how do I kind of run a parallel program across a cluster, right? So try this out, and then we will discuss little finer points about this. The assignment will be available in next couple of days. I think Monday I will try to put it out. So at least you will start thinking about that problem, looking at pi as an example, thinking about how do I do sends and receives, because in pi program I used a little shortcut, uh, and then the uh, simple data parallel computation. Think about how you're going to structure your program, right? Okay, now we have not encountered any failure scenario here or taken into account of failure scenarios. That is another software layer on top. We're not discussing that now. We'll probably bring this up a different uh, session, and maybe I will ask you to enhance your program for fault tolerance. What if a process dies? What would you do, right? That could be a second assignment, for example, when we study more of fault tolerance. Now, at what number of processors MPI fails? Now, that I don't think there's a theoretical bound to it. That depends entirely on your machines. I don't think MPI is going to fail generally across hundreds of processes, but of course there'll be overheads of communication and so on in any cluster. Right now, it's pretty hardware specific when scaling may not happen, but that's something you can't bring up a number like that. It depends on a lot of other factors, right? Okay, so let's stop here. I think we are over time, but I will share this program anyway. It's in the deck, but simplicity for you can cut paste and use it. I'll share this. Please get started with it and start thinking about your assignment when it's rolled out in a couple of days time, because it is basically based on what we covered today in how I discussed OpenMPI, as well as how that program ABC, if you remember, right, that how that structure of data parallel computation happens. Okay, so let's stop here and continue next week, and have a good weekend, and look out for the code on Canvas. Slides are already there. Thank you all.